So here's how you find the maximum and minimum of an equation. Step one, you write in terms of one variable, often the most challenging piece of the optimization steps. Step two, find the first derivative and set it equal to 0. Now, step three we didn't have to do on that problem because the endpoints were 0 on the last problem we just did, the fence problem. But if you had different endpoints like the profit thing, you would have to check them because endpoints don't necessarily have derivatives of 0. So if you look at this example I drew on the board, the derivative here is not 0. Okay? Everybody good on this? Steps? Oh, oh sorry. Why are you going too fast? Going back. Give you a couple seconds to write that down. I'm saving step 3 to more complicated problems. Okay? So checking the endpoints, we'll do that a little later. If you didn't get that, we'll go from there. Here's another great example. I think this is kind of like example 5, maybe from your book, might be a little different from somewhere else. I'm not sure. Here's the question. Every time you go into Pick and Save, you might see like Campbell soup cans. Why are they all the same size? They're all the same size because the people who produce the Campbell soup cans want to use the little amount of material possible so that they don't waste money. So that's why they're not really tall and skinny or short and fat. They want the optimal, optimized, size. So the question is, what dimensions for a 1 liter cylindrical can will use the least amount of material? Okay? So now here's my optimizing part. Least amount of material. Ready, geometry people? Here we go. What shape is that? Cylinder. What kind of thing equation am I going to use to find the least amount of material? Surface area. Okay, circumference would be for a 2-dimensional shape. This is surface area. Can you visualize this can and find out how to find its surface area? Okay, who wants to help me? Okay, Leah.
You need the circumference and the height.
You need the circumference and height. That's it? Yeah, kinda. Okay, somebody want to give me a formula? Anthony?
I was going to say you don't see the top and bottom part 2.
Top and bottom part 2. What are the top and bottom shapes?
Circles.
Circles. So this shape right there is a circle. Its bottom shape is a circle. So I've got 2 circles. Do you know how to find the area of a circle? Heather? Pi r squared. So I got 2 tops and bottoms, 2 pi r squareds. Now the hard part for this is what we call the lateral area in geometry. Anybody know? Chris?
It's just the circumference of the circle.
That's it?
Times the height.
Times the height.
Yeah.
Here is a visual. Mr. Czaplewski is now taking a piece of paper and folding it like a cylinder. Cylinder, ready? Can. Top and bottom, easy. Are you ready? Here, I'm going to unwrap it. A rectangle. If I cut this motor oil down the middle right there, it forms a rectangle. Take a look at its height. This is its height, or base or height. I don't know what you want to call it. Let's call that the base. Let me wrap it. Notice when I wrap it, it's the circumference of a circle. Anybody know the circumference formula?
2 pi r.
2 pi r. And then you need it base times height, so you need it the height of that, so it's 2 pi r h. Okay? So that's, I think, on my next slide.
Wait. I'm just kidding. That was fine.
2 circles right there, plus that lateral area, which is an unrolled up rectangle. I did this with my advanced algebra classes. If you had me, we did this exact same problem similarly last year. I did that exact same model. Okay, everybody okay on that? Is there any questions? Yes?
For other formulas, when we're doing problems like this, can we,
You can use your book right now, but remember on the AP exam, writing these formulas, you won't have to. So they won't require you to do this, but I will, and I'll give you most of them. However, I do expect you to know circumference of a circle. I do expect you to know area of a circle. I do expect you to know triangles, trapezoids, and rectangles. And I expect you to know trigonometry and Pythagorean theorem. Okay? It's a lot, but it's not that bad. Come on. Okay, what's wrong with this equation? 2 variables. I wonder if I could use the problem to get rid of one of them. 1 liter. Didn't use that yet. Now, 1 liter, what kind of measurement is a liter? Is it length? It's volume. So I need to go to volume formula. pi r squared h.
Oh.
Okay? And by the way, a volume of any regular item is the area of the base times the height. So now, and then here's a conversion. You won't have to do conversions on the AP exam. If I had this problem for you, I would probably convert it to 1,000 cubic centimeters. Okay? And remember that cubic centimeters is a measurement of volume, so you go to volume, plug in 1,000 for V, solve for one of your letters. Go! One more time, plug in 1,000 for V, and solve for one of your letters in terms of the other, and plug it back in, so you only have one variable on the right side. This is what I solve for. I hope I'm not going too fast. Could you have solved for R? Sure, but it's more messy because you have square roots, you have pluses and minuses. Ugh. Yeah, but you still have pi this way. Now I take this guy, substitute it in for h, and now I have only one letter. If I were to look at a graph of this, it would be surface area on this axis, it would be radius on this axis. If the graph looked like this would be the top of the graph, which its derivative equals 0, so on and so forth. So moving on to the next slide. After you get a function of one letter, oh, and simplify. Oh, I forgot to simplify. Simplify. Because we're about to take the derivative. That's always the next step. If you don't simplify, your derivative is often harder. How am I doing? Am I losing you? This isn't bad, is it?
So A is surface area.
So A, yeah, I would have said S of A, but the guy I copied this from is just a A guy. I like surface area. Okay, now I rewrite it like this. Derivative me. Once you get the function that's simplified, derivative me. If you really wanted to, you could get common denominators and combine them, but you don't need to. And notice how I changed it to A prime. Any issues there? Yep, Sophia.
Pi is a number, so isn't its derivative 0?
It is, but it's the same thing as taking the derivative of 3x. The derivative of 3x is 3.
Yeah.
The derivative of 3x squared is 6x. So you take this 2, you multiply it by 4, your constant is not 4, it's 4 pi.
So pi acts as x.
It acts as like 4 times 3.14 or 2 times 3.14, so this is like 6-ish, and this changes to 4 times 3, 12-ish.
Okay.
Okay, we good? After you take the derivative and set it equal to 0, did I set it equal to 0? I don't think I did. There it is, 0. What do we do now? Solve for R. My philosophy is to bring this to the other side, but you can do it however you want. So when you bring this guy to the other side, whoops, you get to this at the top. And then I probably multiply both sides by R squared. Solve for R. Yeah, you'll have to use a calculator in this one. You'll have to take a cube root. They reduced 2,000 fourths to 500. So 500 divided by 3.14159, take cube root.
5.4.
Yeah, in 3 decimal places, I don't like that slide. Okay, Sophia.
When you have a problem where pi is in the equation, when you're reducing and solving, do you want to keep pi as you're solving?
Great My suggestion on handling pies and e's, keep them till the end. Because if you round it here, then your rounding error will change here, and it changes here, and it keeps changing. Keep it to the end, don't round it till you've answered the question. Now, what was the question? What dimensions? We've got a radius, a really nice radius. How tall is the can? We don't know, how do you figure it out? Plug it in right there. Always go back and answer the question. So I got one more to do after this, so I'm wrapping it up. So I need a can with a radius of 5.42 centimeters and a height of 10.83. Once again, I don't like the slide because of its decimal issue.